So again, if calcium is a metal, where's bromine at? You said it's a halogen, so where's that at on the table?
The seventh column.
Okay, so therefore, is that a metal or a non-metal?
A non-metal.
Okay, so if we have bonding taking place between a metal and a non-metal, it's the very first thing we talked about yesterday. What type of bond is that? Is that covalent or ionic? Is it covalent or ionic? I mean, you can look back at your handout and say, oh, it says that ionic bonding takes place between a metal and a non-metal, and that's exactly what we have here. Okay, so we're going to start with calcium in the middle here, because what column is calcium in? You said
The second column.
alkaline earth metals, that means the second column. Okay, so we can go ahead and put a dot here and a dot here. Okay, so that must mean, just like what we did here, we had a triangle and an X, a triangle and X. That must mean we can put a bond there. So we can also put a bond where these dots are. And that's exactly what we're going to do with one bromine atom. And again, what column is bromine in? So how many valence electrons is that? So if it's in column 7, how many more electrons does it want? If it's in the 7th column, how many more electrons does it want?
7.
If it's in the 7th column, how many more electrons does it want? Just 1. And where might one of these bromines get an electron from? What's your only option? Where can a bromine get an electron from?
The second column.
Okay, here's our bromine. 7th column, 7 valence electrons. This wants one more. Where could it possibly get that from?
Second column.
Not the 2nd column, not the 1st column. From the calcium. Okay? So what we could do is like if you're using a Word document or you're taking a picture, you click on it and bring it up and set it down. So we're taking this and putting it up here. This now has 8 electrons around it. Okay? But that's just one bromine atom. How many more are there in the formula? We do one on the other side, just like you had mentioned. We could put one here. Now, calcium doesn't have any around it. So is it stable then? Yes, it is, because it has 8 valence electrons around it. Okay? Well, how would we know that? Well, prior knowledge tells us we've got 20 on the inside, 20 protons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Well, one electron went here, and then another electron went here. So those are now gone from the calcium. So these are gone. So does it have 8 electrons in its outer energy level?
No.
Yes, it does. 2 plus 6 would give you 8. So the calcium now is stable, even though it doesn't have any electrons around it, because it gave those away to the bromines. Okay? So we're going to take a very similar concept to this called beryllium hydroxide. Kind of looks like googly eyes, don't it? Kind of. So I'm going to, so it doesn't look like anything's looking at us. There. That's better. Okay, So what column is beryllium in? Element number 4.
The second column.
So how many valence electrons is that?
2.
Okay. So what did we do with calcium? How many electrons did we give that?
2.
Because it's in the same column. So we're going to do the same thing. I'll use triangles this time. Then how many oxygen atoms do we have? Not electrons. How many oxygen atoms do we have?
8.
2 is correct. Why? Because it says 2. You have to distribute that inside the parentheses. Okay? So 1 oxygen atom. What column is oxygen in?
This 8, 6.
The 6th column. So how many valence electrons is that?
6.
Okay? So that must mean we can put an oxygen here, make a bond. 1, 2, 3, 4, 5, 6. How many more electrons does oxygen want?
2.
It only wants 1 more because it has 7 around it, right? Because it got one from the beryllium. Okay? So where could it possibly just get 1 electron and 1 electron only? What's left in our formula here?
Hydrogen.
Hydrogen, and it's in which column?
First.
So how many valence electrons is that?
1.
Just 1. So we could make a bond here and say there's a hydrogen atom. And you don't have to put boxes around these, but you can. Okay? So we had 2 oxygen atoms. We took care of 1. Where might the other one go? On the other side. Because there's a lone triangle here. So we can do the same thing. So this oxygen now has how many electrons around it? Right now, how many electrons are around here?
6.
How many total electrons are around here?
7.
There's 7. So it wants 1 more. Where could it get that electron from? There's still a hydrogen left. Okay. And for the same reason, calcium was stable by giving its electrons away. Beryllium is also stable by giving its electrons away. This is also an ionic bond. Okay? Back row, are we on the bus? Back row, are we on the bus? Oh, very good. I mean, thumbs up, we like to see that. Middle row. Front row. Okay? So we'll move on to this. Let's start with our carbons. Carbon is in which column? Yes. Yes. 4th column. Okay? So how many valence electrons is that?
4.
Okay? So we just go ahead and use dots. 1, 2, 3, 4. Okay? So how many chlorine atoms do we have?
4.
Okay? So where can we possibly form bonds on this carbon? How did we know we could form bonds on this beryllium, on this calcium, or on this phosphorus? How did we know where we could put a bond?
Chlorine.
Well, it's going to be chlorine. And where could we take 1 chlorine atom and make a bond?
7.
It's in the 7th column. So let's go ahead and look at chlorine, 7th column. How many more electrons does this chlorine want?
1.
And where would it get that electron from?
Carbon.
On the side of carbon. So we could pick this up and set it down here. Okay? So now we're down to 3 chlorines because we've taken care of 1. What might we do here? We haven't put another chlorine atom there. 2 down, 2 to go. What else could we do? We could do the same thing. Put another chlorine atom here. And then for space purposes, we've taken care of 3, we have 4. You could put another chlorine atom up top. And what that would look like, make a bond, just really, really small. Okay? This one, these two were probably the most difficult. This one's probably more difficult than that one. But do you want to try to tackle that on your own? Okay, so do you want to see just what the answer is or the logical approach that you would probably take? So the approach would say carbon is in column 4. So since it's in column 4, how many valence electrons is that?
4.
Okay, so this is the logical approach that you would maybe take. So there's one carbon atom. Let's go ahead and make a bond with another one. Okay, so is there any similarities between bromine and chlorine on the periodic table? Is there any similarities with those two?
Yeah.
Yes, there is.
They're on the 7th column.
They're both in the 7th column, so they both have 7 valence electrons. So if we change this to bromine, we could take this and set it down over here, right? Because there's an availability for a bond to take place, right? Would we agree? Okay, we're nodding our head yes, so let's try that. Okay, there's one bromine. Okay, so let's go ahead and put one over here to balance it out. Okay, there's 2 bromines, 2 down, 2 to go. Where can we put another bromine atom on these carbons? Top or bottom?
Top.
Okay. Okay, 3 bromines down, 1 to go. Left or right carbon? Okay, so there's an availability to bond on this one, top or bottom? Okay. We're all out of elements now. Is there a problem with this bromine? How many electrons does it have? Yeah, so that should be happy, right? Okay, what about this bromine? This one. And then this one. Okay, what about this carbon then? There's only 7. So that does not work. But what is something that carbon can do that many other elements cannot? Say that again? Share, and yeah, they would be sharing them now. But we tried to illustrate this, a single bond. That did not work. What else can carbon do that other elements cannot?
Split it like 3 ways.
That can't really split 3 ways. And we talked about this yesterday, talking about some elements going to first base, second base, third base, which means first base is a single, second base is what?
Double.
A double. So we can do double bonds then. Can carbon do that?
Yes.
Yes, it can. Can carbon triple bond?
Yes.
Yes, it can. Okay? So what that means then, Let's try a double bond then.
Is that for the eyes?
Nope. We're still dealing with, because this doesn't work. Okay? So then, what do you suppose might happen where we see a lone X and a lone triangle? What could we bond there? Because here's a bromine atom with 7 valence electrons. How many does it want? It wants to have 8. It's got 7, so it wants how many more? And where could it get that from? Well, wherever there's a lone electron, we could put a bromine atom here. Okay, where else could we bond one? So 1 down, 3 to go. Yeah, so wherever there's another opening here. And you can use ease if you want. Okay? 2 down, 2 to go. What do you suppose would happen here and here? Yeah, go ahead and put your bromine atoms there too. 3 down, 1 to go. So what would happen down here? Yeah, add your final bromine. Again, you can use X's, triangles, E's, slashes. And when you do it in this fashion, it just shows you which electron is coming from which element then. Middle row, are we on the bus here? Middle row. Middle row. Okay, front row. Back row. Okay, so we will go ahead and continue with chemical reactions from public television. And your worksheet that was supposed to be assigned today, we will hand that out on Monday. Your vocabulary will be assigned on Monday. And then your worksheet will also be assigned on Monday.
Like cotton balls? Yep. Now, you might think that cotton balls don't explode. And you'd be right. That was underwhelming.
This was just regular cotton.
Cotton fiber is about 90% cellulose, a key structural component in green plants, composed of carbon, hydrogen, and oxygen, but no nitrogen. So our cotton balls will burn, eventually, though not explode. The spores are erupting! But back in the mid-1800s, chemists discovered that they could add to cellulose what are called nitro groups, each a nitrogen and 2 oxygen atoms. That turned it into nitrocellulose, also called gun cotton. Those nitro groups made something that burns like this into something that burns like this. Flash paper. But nitrocellulose is no joke. In a confined space like a gun barrel, it can be powerful. It was the propellant the military used to launch the shells out of these 16-inch guns on Iowa-class battleships. And it's still a propellant today in 155mm artillery. Our next test, is 50 pounds of nitrocellulose propellant, the kind used in those large bore guns. We give you 50 pounds of gun cotton. Since the sphere container isn't sealed, it won't explode, delivered unto the Earth. But what will happen? After Jonathan wires it up, we head to a nearby bunker to find out.
Here we go. 3, 2, 1.
Compared to plain cotton, this is a show. The burning nitrocellulose generates rapidly expanding gases, including carbon dioxide, carbon monoxide, water vapor, and of course, nitrogen. It's pretty. Packed behind a shell in the barrel of a gun, the pressure from the expanding gases would hurl the shell forward. In our open bowl, it's more like fireworks, with the gases sending burning pellets up in the air.
That's just a propellant. That's a low grade here. We're going to move on to actual explosives now.
Oh yeah?
Yeah.
What's first up?
So we're going to start off with ANFO.
ANFO.
That is the biggest mining explosive that we have.
Oh, cool! ANFO is an industrial explosive used in mining and construction. It accounts for about 80% of all the explosives used in North America. Probably no chemical shows better the intimate relationship between fertilizer and explosives. Though the name ANFO stands for ammonium nitrate and fuel oil, it's over 90% ammonium nitrate, the same stuff as synthetic fertilizer. Ammonium nitrate is built around nitrogen atoms, so it packs way more nitrogen than nitrocellulose. That means ammonium nitrate can be very dangerous. This is the aftermath of the deadliest industrial accident in U.S. history. The explosion of over 2,000 tons of ammonium nitrate aboard a ship in Texas City, Texas in 1947. In 2020, in Beirut, Lebanon, there was a similar explosion. A waterfront warehouse containing thousands of tons of ammonium nitrate caught fire and detonated. The blast killed over 200 people, injured thousands, and left an estimated 300,000 homeless. Our ANFO test will be just 50 pounds of the stuff.
50 pounds.
To get a reaction going, even one that will release a lot of bang, you need to put some energy into it first to get some of the bonds to break. That's called activation energy. This is nitrogen triiodide, an explosive whose existence is so precarious, minimal activation energy is needed. Even just the touch of a feather. In contrast, ANFO is hard to set off. So Jonathan hooks up a booster, a smaller explosive. Since much of Emertech's research and training involves explosions in human-occupied environments, they typically add a wooden dummy for scale and to demonstrate an explosive's effect.
You good? Okay, here we go. 3, 2, 1.
That, my friend, is a firecracker. That was like 7 stories. So, what just happened? Jonathan ignites the booster. That's the black smoke you see. The pressure wave from the exploding booster in turn detonates the ANFO, breaking the bonds holding the ANFO atoms together. They rearrange into more stable gases, nitrogen, carbon dioxide, and water vapor, along with some carbon monoxide and nitrogen oxides. The hot gases rapidly expand, creating a supersonic shock wave traveling at about 2 miles per second. If you look at just the nitrogen atoms of the ANFO, it's like the unhopper process. Most of the nitrogens from the ammonium ions and nitrate ions reunite into their more stable preferred state, N2. In fact, about half of the power of the ANFO explosion comes from nitrogen atoms reforming into nitrogen molecules. Here we are, what, a quarter of a mile away? And you could feel the ground shaking.
Yep.
And that's 50 pounds.
That's only 50 pounds, yes.
Next up, you've seen it in movies. And you probably even know its name.
What's that? It's C4.
And just one look at its active ingredient should tell you we've upped our game. Cyclotrimethylene trinitramine, commonly known as RDX. While it has 3 nitro groups, there's even more nitrogen built into its ring. And even though the nitrogen triple bond is one of the strongest in nature, the single bonds between the nitrogen in the ring and the nitro groups are rather weak, often the first to fail when detonated. Oh my. The last one for the day for us.
Yeah, 50 pounds of C4.
All right. Should I be offended that they've dressed him like me? Is there a hidden message in that?
I wouldn't take it personal, but, you know.
All right.
Oh, wait, I gotta go do that.
Oh, but it looks so cool.
I know, Charging. Okay, here we go. 3, 2, 1.
When the detonation pressure wave hits the RDX molecule, the ring compresses and then flies apart. The atoms recombine into carbon monoxide, water vapor, and nitrogen gas. Those reactions produce far more heat than ANFO does, which makes the gases expand much more rapidly, giving RDX over twice the explosive power.
So we have more heat and energy in there.
There's more nitrogen in there.
Exactly.
Does that mean that the future is just all nitrogen?
That is the goal. We are trying to make entirely nitrogen-composed explosive molecules.
Here's one from the drawing boards with a great name, octaazocubane. Entirely made of nitrogen, it is predicted to have a faster velocity of detonation than any known non-nuclear explosive, if someone could just figure out how to make it. I think that's all that's left. And so ends our day of the un-Haber-Bosch process. Much of the nitrogen in our explosives has returned to its happy, or at least extremely inert state, as N2 molecules in the atmosphere over New Mexico. In chemistry, reactions tend to consume other ingredients, transforming them into something new. That's the process that chemical equations are designed to explain. But in biology, molecules can sometimes bind to each other without consuming or producing anything new. They can act as triggers or messengers. Or, as it's sometimes described, like a key fitting into a lock. To learn more about molecular locks and keys, I've come to experience them viscerally.
Oh, wow.
Here at the Burke's Pepper Jam in Bethel, Pennsylvania.
Smell that.
An annual festival of food, entertainment, and contests, all centered on chili peppers. Reaper Evil hot sauce. They do have an ambulance on hand, right?
They do.
When it comes to peppers, I'm a novice. But the first thing you need to know is that the black pepper you see sitting with salt and chili peppers have different chemistries and histories. Black pepper is the dried ground-up fruit of a flowering vine native to Asia. Its kick comes mainly from the molecule piperine. While one side of the world had black pepper, the other side had chili peppers, first domesticated by Mesoamericans and then traded around the world by European explorers. The main active ingredient in chili peppers is the molecule capsaicin. More on that in a bit.
3, 2, 1, eat!
The jam features a pepper eating contest for kids, but they wouldn't let me in. So I plan on entering the one for adults after I get some advice.
I've actually never eaten a pepper by itself.
Bow out when you feel you should.
Really?
Raw pepper is a completely different deal. I can't do it.
You can't eat a Reaper? Is there any way I can prepare?
You got your will made out? You don't have anything to do for the next 3 days, do you?
Yeah, you're gonna feel great Monday morning.
A big round of applause for Lizzie. Well done.
Time to put my tongue to the test.
Long hots. Red Fresno.
Here's how the contest works. There are 10 rounds of increasingly hot peppers.
Peach Copenhagen. Big Red Mama.
Their spiciness measured on a scale invented in 1912 by pharmacist Wilbur Scoville. It estimates the amount of capsaicin in each pepper. Contestants have to eat a pepper and then wait 2.5 minutes to allow the burn to grow. If they drink the milk in front of them, a popular way to douse a tongue on fire,
They are eliminated.
they're out. My competitors include some rugged-looking characters. And Leah,
I've never done this before. I figured this out 2 hours ago.
a 15-year-old who entered with the permission of her parents.
We begin our contest with the long hots. Let's turn up the heat.
And we're off.
Zesty, with just a hint of poison.
Round 2, we're going to start with the red Fresno pepper. Eat, 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 eat.
Gotta be some easier way to learn about molecules.
All right, are we ready? Eat.
That was not designed for human consumption.
Round number 4, habanero peppers.
Parts of my body I didn't know I had are on fire.
10 more seconds. You got this.
I can't.
Don't do it. No! The orange Copenhagen pepper.
What am I doing? Oh man. Oh my god.
Don't do it.
I want it! Wherever you are, Scoville, I hope you rot. Cheers!
No!
So, I'm the first to fall.
Is there a porta potty?
But there's a bigger mystery. How does a pepper's capsaicin convince my mouth it's on fire?
Not recommended.
I think I'll...
Okay, we can continue with that, finish that on. How many would like to enter a contest like that, or would even have that ability? I don't think I could either. All right, so we'll catch up to you next time.